We'll start. Yes. Okay. So the topic of today's video will be again heat equation, but the case will be changed when the ends of the thin rod are perfectly insulated, right? Together with this curved surface area is also insulated. You know that. Let me write that case. Only boundary conditions will be changed. Heat equation. Case 2. Heat equation is C square Uxx is equal to ut, and you know that the C square is actually equal to capital T over rho into sigma, where the symbols have their usual meanings, right? And subject to the first boundary conditions are del u over x 0 comma t equal to 0, and the second boundary condition is del u over del x L comma t equal to 0 for t stands for time greater than 0, right? And third, that is initial condition that depends on time, right? That depends on t is equal to 0, initial time, and that is u x comma 0 is equal to fx, right? Now you can see that we are discussing the case when the ends of the rod are perfectly insulated. That is different from the case we discussed in our last video when the ends were maintained at 0 temperature. In this case, ends are also insulated together with this curved surface, means the whole rod is insulated, right? And what do we mean by this when we say that both the ends are insulated? It means that there is no heat flow along the x-axis at any end, right? Because at each end is perfectly insulated and there cannot be any rate of change of heat along the x-axis. See this. What does this mean? This means that at your left end, that is x is equal to 0, the change of temperature along the x-axis is 0, right? And by this condition, you mean that at the right end of your rod, the change of temperature with respect to x all along the x-axis direction is 0, because both the ends are perfectly insulated. No heat can escape through both these ends. That's why del u over del x at both ends should be equal to 0, right? And this is the same condition we were using, that initial temperature distribution. The rod has to be maintained at some temperature initially in order to allow the flow of heat throughout its length, right? So this is the initial temperature conditions, and these are two conditions for ends, boundary conditions, and this is called initial conditions. And remember that in contrast to the wave equation, where this is uxx and utt, means second order derivative with respect to x and second order derivative with respect to t, there were 4 conditions, 2 boundary conditions and 2 initial conditions, while in heat equation we don't need 2 initial conditions, we need only 1 initial condition, and it is due to the fact that this equation is a first order PD in terms of t. If you hide this term, you see, focus on this derivative. This is a first order derivative, and for first order differential equation, you just need 1 boundary condition. 2 boundary conditions are not needed, otherwise they may give a no solution, right? Okay, so we'll proceed with the solution as we discussed in our last video, and since these 2 conditions are different, so I will be taking the most general solution. Means I will be starting with u is equal to solution of this. Let u x t is equal to xx dot tt be the solution. Let me call it equation number A, solution of this wave equation, and then I found del square u over del x square and del u by del t. Then I plugged those values here. Then I will get something like this. This gives, on plugging in my heat equation to ODE, that will be 1 over, I should write them directly, right? One was x double dash, and I think here I had plus p square x equal to 0, and this other was t double dash plus c square p square t equal to 0, right? Fine. Yes. And you know that what is this p square? P square is actually the value of separation constant. K is equal to minus p square. If you remember that in the original derivation of this heat equation. Okay, then I got two solutions. One was then x as a function of x. I got C1 cos px plus C2 sin px, and from here I got Tt is equal to e to the power minus c square p square t. Okay, fine. Then I will plug these x and t here in my solution. Therefore, u x comma t, I should write a constant here. I think that should be C3, right? Then on multiplying these two, I will be getting something like this: a cos px plus a cos px plus b sin px multiplied by e to the power minus c square p square t, and where I have replaced the constant C1, C3, the product of C1 and C3, it's replaced by capital A, C1, C3 equal to capital A, and C2, C3 equal to capital B, right? So I have two arbitrary constants here. Fine. And yes, this is the most general solution. I will start with this solution, impose these conditions on it, and then find the solution, right? So focusing on this condition number first, and this will need del u over del x. I have to differentiate this with respect to x, and that will convert this cos into sine and this sine into cos, and then putting x is equal to 0 here, I think this term will be 0, and from that I will be getting using let me call it equation number 1, because this is my most general solution, right? Using condition number 1, that is ux 0 comma t equal to 0, and you can differentiate it with respect to x. Okay, sine, and that will become 0. That will give b times p sine, and then sine will become cos 0 will become 1, fine, and e to the power minus c square p square t equal to 0, right? I have differentiated it and substituted x is equal to 0, right? I have written it directly, and now you can see that either b will be 0, p will be 0, or this exponential function 0, but this can never be 0 being an exponential function. So you have to take this capital B is equal to 0, right? And on taking capital B is equal to 0, give this, or B equal to 0. So B is equal to 0. Then plugging this B is equal to 0 in my equation number 1. Therefore, u x t equal to a times cos px e to the power minus c square p square t is the refined solution with the lesser number of constants, right? Now on imposing condition number 2, using second condition, that is u x l comma t equal to 0, right? And if I differentiate this with respect to x, then it will become sine px, right? And okay, fine, that will gives a times p, and that will become sine pl, I think, sine pl, and this will be e to the power minus c square p square t equal to 0. And I have rejected that negative sign because that is immaterial, right hand side is 0, fine. Then you can see that if you take a is equal to 0, right, if you take a is equal to 0, that will reduce this solution to a 0 solution, and we don't want a 0 solution. And if you take this p is equal to 0, again that will reduce to u is equal to capital A, constant solution, and that will not be the robust solution. We are seeking the robust solution. By robust, what do I mean? I mean a strong solution, a solution having more and more number of constants, right? That should be more general in nature. So taking p is equal to 0 will not be a good choice, because putting p is equal to 0 here will produce u is equal to a constant solution, right? And that is not robust solution, not a strong solution. So you have to take sin pl is equal to 0, which implies pl is equal to n times of pi, because sin is 0 for integral multiples of 2 pi, integral multiples of pi, where n belongs to z integer, and that will give me, I think this was capital L, sorry, capital L. That will give me p is equal to n pi over L, and n belong to integer. Fine. So value of p is determined now. I can substitute the value of p here. This solution, this is my refined solution, equation number 2. Therefore, equation 2 becomes ux comma t equal to, putting this value here, a cos n pi over L, and x is right, e to the power minus c square n square pi square over L square t is solution. And you know that these n are integers, right? So I should write here n is an integer. Okay, and let me write a summation here, or first I should investigate the case for n is equal to 0, because earlier we have seen that n is equal to 0 case is rejected, because that gives a 0 solution. We will see that whether n is equal to 0, because n is equal to 0 belongs to this set. So putting n is equal to 0 here, what will happen? We will get a constant solution, and that is indeed a solution. As I discussed that constant u is equal to capital A is constant, but that is not a robust solution. This is a robust solution containing the more general solution, and putting the n is equal to 0 is giving a constant solution, not a 0 solution. So n is equal to 0 will be accepted here, in contrast to the last case we discussed. For the ends maintained at 0 temperature, we rejected n is equal to 0, right? But here we have to accept that n is equal to 0, because that is not producing the 0 solution, right? So I have to take n is equal to 0, and obviously 1, 2 and 3 are also allowed, right? But what about the negative values of n? And you can see that if I put n equal to -1, what will happen? Cos -1, right? And cos minus theta is cos theta, so no need to write minus 1, -1, -2 and -3 and so on, because this solution is insensitive for the negative values of n. What do I mean by insensitive? Putting a negative value of n will do nothing. That will again convert the solution into this form, because cos of minus theta is theta, so there is no need to write the negative values of n. Fine. And you can see here that here we have n square. Again, this is insensitive to the negative values of n, right? So this is the most general solution. But if you don't need to, first I should write here the y. You should know this step, reason for this step, reason for this, especially this n is equal to 0, right? And now you can see that you can write it in summation form as ux comma t equal to summation, and now my summation n equal to 0 to infinity, because 0 is included here, and cos, and here we have this a n. I should write the a n, because again, since the equation is a linear equation, and every solution of this form, right, can be added in terms of linear combination. And what do I mean by linear combination? You have one solution, you multiply it by some constant. You have second solution, multiply it by second constant, and then add. That's why I am writing it as a n, right? You can change the constant. A n cos n pi x over capital L, and here I have c square n square pi square over L square t is the solution. It is the most general solution containing constant solution also, or you can substitute n is equal to 0 here to write in this form, or u x comma t equal to, putting n equal to 0 here will give me a naught, and cos 0 becomes 1, e to the power 0 becomes 1, and then running the summation n equal to 1 onwards, a n cos n pi x over L, and here e to the power minus c square n square pi square over L square t, right, is solution. So I will box this solution. I will be going to use this solution, right, and you can see that this is a naught and a n, right, and still one condition is remaining, third condition, right, and to use that third condition, if I put ux 0 means t is equal to 0, I will put here, then this will be replaced by fx, then I have to use again that Fourier sine series. Should I write that? Okay, using third condition, the initial condition, that is u x comma 0 equal to fx gives, that will give me fx equal to a naught plus summation n equal to 1 to infinity, and that will give me a n cos n pi x over L, okay, right, and you can see that this is a Fourier cosine half range series. So this time we have cosine here, right, cosine series, and see this constant, and you know that by Fourier coefficient you should have a naught is given by 1 over capital L integral 0 to L fx dx, and this a n is given by 2 over L integral 0 to L, and here we have fx cos n pi x over L dx, right. These are the formulae which are used in Fourier cosine half range series. That was the part of your syllabus in previous semester. Okay, fine. So the solution will ultimately take the form, if I substitute these a naught and a n here, that will take the form, then the final solution uxt is equal to the value of a naught is this one, 1 over L and 0 to L fx dx plus this summation n equal to 1 to infinity, and the value of n is this one, 2 over L integral 0 to L fx cos n pi x over L dx. This is the value of a n, and then cos n pi x over L multiplied by e to the power minus c square n square pi square over L square multiplied by small t. This is the required solution, the most general solution, using every condition, first, second and third conditions. All conditions are incorporated in this solution, right, and you can see that if you approach this small t to infinity, right, approaching a small t tending to infinity, then what will happen? Since e to the power negative, this number always is negative, is one minus of infinity, that will, this part will go to 0. If you approach time to infinity, means after infinite time this term will go to 0. You are left with this constant term. This is a constant term, 1 upon L is a constant, and this is a definite integral with a constant limit. This will be a constant, right. So I should write here that as t tends to infinity, right, limit t tends to infinity, u x comma t will become ultimately equal to 1 over L 0 to L fx dx, right. And what does it mean? That when the time becomes infinite, or after a large time, the temperature of the rod will be a constant. And if you watch this closely, this is actually the average, or you can see the mean value of the function taken on the interval 0 to L. If you remember the average value of the function, I will tell you, if fx is a function defined on a closed interval a to b, right, then its average value is given by integral a to b fx dx divided by the length of the interval, and that is b minus a, and that is indeed the same thing here. You can see that fx dx integrated over the range of the interval 0 to L and divided by the length of the interval L minus 0. So this is actually the mean value of the initial temperature, right. is equal to mean value of fx over the interval 0 comma L. And what does it mean? That it means that your initial temperature distribution was fx, right, initially, but after a large time your temperature of the rod is equal to constant, and that constant is equal to that function, that average value of that function, right? Means the temperature gets uniformly distributed over the length of the rod after infinite time, right? And if you remember our last case, that was the rod with its ends capped at 0 degree temperature, right? In that case, if you remember, that the solution was containing the sine term. In spite of this cos term, we had sine here, and this was absent, right? If you focus on this thing, then here we had sine and this was absent, right? Because in that case n equal to 0 was not allowed, and since n equal to 0 was not allowed, so this term was 0 there, right? Fine. And for that case, this will be absent for the case when the ends are capped at 0 temperature. Fine. And if you allow t tends to infinity, in that case when this term is absent, then uxt will become 0. Fine. And what does that indicate? That if the ends of the rod are kept at 0 temperature, then after infinite time the whole rod will be at 0 temperature, right? Means that whatever is your initial condition, right, after t tends to infinity, that initial temperature function, right, that initial temperature function fx becomes uniformly distributed over the whole length of the rod. And there is the fact you can see from here, this mean value of fx over 0 to L, but this happens after sufficient large time, right? Fine. So I will be taking numerical of this case when the ends are kept at insulated ends. So I will rub this. Okay, example number 1. Solve u c square u xx is equal to ut subject to first condition u x 0 comma t equal to 0, second condition u x L comma t equal to 0, and the third condition u x comma 0 equal to let me take x multiplied by L minus x, and obviously these two conditions are for t greater than 0, and this condition is for 0 to x to L. Fine. Okay, so now you can see that the ends are perfectly insulated, right? What do you mean by this? Ux at 0 t is equal to 0, ux at L t equal to 0 means the ends are perfectly insulated. Fine. So starting with the most general solution, I should take the solution from here. I can use this equation also, right? Because this is having all of these three conditions, I think. What do I need to do now? Just replacing this fx by this thing. This is my fx actually, is equal to fx. Okay, and that will be an easy task. Okay, or should I start from taking these two conditions only? Okay, solution. The solution to c square uxx is equal to ut after using condition number 1 and condition number 2. I am writing the solution for these two conditions. Okay, and the solution should be ux comma t equal to what we had. Okay, that solution, this solution, using only two conditions, a naught plus summation n equal to 1 to infinity a n cos n pi x over L multiplied by e to the power minus c square n square pi square L square times t, right? So this is the solution after using condition number 1 and second. I have written that directly from this theory. Fine. Now using this condition number 3, using condition number 3, and for that I have to ux is 0, putting t is equal to 0, right? Put t is equal to 0 here, and that will give me x L minus x is equal to fx is equal to, putting t is equal to 0 here, a naught plus summation n equal to 1 to infinity a n, and putting t equal to 0. Fine, this will become 1 cos n pi x over L. Fine. And since this function has been expressed as a sum of cosine functions, so this is similar to the half range cosine series, Fourier cosine series, and then the coefficients of that series are given by, we have formula 1 over L integral 0 to L fx dx and x L minus x dx. Now I have to integrate this, right? And on integrating this, I will be getting, that will be xl, and I think x square by 2, fine, 1 over L and x square L by 2 minus x cube by 3, and we have 0 to L, putting L cube by 2 and L cube by 3, I think L cube by 6, and that will give me L square over 6, because 3 L is present here, if I am not wrong. Yes, okay, fine. So a naught has been calculated, and that is constant, fine, and that has to be a constant from this formula. So you can see that this is a constant, right? And that should be equal to the mean value of the initial temperature distribution. You can check that. And a n is equal to 2 over L integral 0 to L x times L minus x, and this is cos n pi x over L dx. Now I have to apply integration, first function, and integration of second function, sine n pi x over L divided by n pi over L, and then minus the differentiation of this thing will be L minus 2x, and integration of this will be minus cos n pi x over L upon n square pi square over L square, and again plus differentiation of this will be minus 2, and integration of this will be minus sine n pi x over L upon n cube pi cube over L cube, fine, and limits are 0 to L. Now you have to put upper limit, and that will produce 0 here, right? And here we'll have equal to 2 over L, this will be 0, let me write it 0, and this will be negative of L, and that will become positive, and again that will become negative, so negative of L, and this L square will go in the numerator, L cube over L square pi square, if I am not wrong. Yes, fine, and this cos will become L, cos n pi, and cos n pi is actually equal to minus 1 to the power n, right? Cos of n pi is equal to minus 1 to the power n. I have written that value directly, and putting L here will produce 0, because sin n pi will become 0, fine. Okay, now this was the result after putting upper limit, and now I will put lower limit. 0 will give 0, 0 here will give me, I think, minus L plus L, and that will become L cube over n square pi square, and here I have what, 0, cos 0 is equal to 1, fine. So ultimately it will become L cube over n square pi square, because cos 0 is equal to 1, and putting 0 here will give me 0, fine. Now in solving this, I will be getting, I think, L cube over n square pi square can be taken common, and that will become 2L square n square pi square, fine, and here I will have minus can be taken common also, minus and minus 1 to the power n, and here I will have plus 1. Fine, right? And remember that this summation, this an was for n equal to 1, 2, 3 and so on. This is not for n equal to 0. So keep in mind that this is an, and an is defined for n equal to 1, 2 and so on. So here I should write it here, n equal to 1, 2 and so on. Fine. And then plugging these values here, where is the solution? I think this is the final solution. Here will give me the final solution. And you can see that if you put the odd values of n, 1, 3 and 5 so on, this will go to 0. And for even values of n, 2, 4 and so on, I think this will become 2 here and that will become 4 and so on. But n square is still present here. Means that odd values of n, this coefficient will be 0. Fine. So I will substitute this a naught and an in my last solution. Okay, let me call it equation number 1. Fine, now I have to rub this. Therefore, equation 1 gives u x comma t, the value of a naught, and that is actually, what is that? L square over 6. L square over 6 plus, and then we have summation n equal to 1 to infinity, and we have this an here, minus twice of L square over n square pi square, and this is multiplied by minus 1 to the power n plus 1, and then we have this cos function, cos n pi x over L, and then e to the power minus c square n square pi square over L square times t is the solution, right? And you can obviously reduce this solution for only even n, because for odd n this is 0. So you can write here for even n, you have to write here 2k, n equal to 2n, right? And there is another way to write the solution, but this is fine. Okay, now I will take another example, but something different. If I change this condition, means one end condition, if I change the left hand condition or right hand condition, if I change right hand condition, then what will happen? See, taking another example, example number 2, and let me try take solve 1 over 4 u x x4 equal to u t is subject to first condition. If I take the left hand side, let me take the left hand side insulated, while the right hand side maintained at 0 temperature, and this is a kind of mixed case for case number 1 and case number 2, means the left hand side is insulated but right hand side is kept at 0 temperature, right? Okay, so left hand side is kept insulated, so that's why I have to write ux 0 comma t equal to 0. It indicates that the left hand is insulated, and but right hand is not insulated, that is kept at 0 temperature, and for that I have to write L comma t equal to 0, and this is for t greater than 0. Fine. And let me take the third condition as initial temperature distribution condition. Let me take this temperature. Okay, fine. Let me take it x10 minus x, or should I take it if I take it like this, x, and if I change this, let me change this length, let me take this length 2 pi. Fine. Okay, then this is for 0 to pi and 2 pi minus x for pi to 2 pi. Let me check that it is continuous pi. Yes, it is continuous. 0 pi. Fine. Right. So in place of a small c, I have 2. If you compare this equation, we have c is equal to 2, and in place of L, that is the length of the rod, I have taken it as 2 pi, right? And this is a kind of a triangular wave function inside the rod. Fine. Okay. So starting with the solution. The solution to this equation, 4 times u xx equal to ut, without using any of these conditions, because this time I don't have these conditions imposed on my solution directly. So I have to write that raw solution, a robust solution, and that was u x comma t, that is containing constants. Okay, a cos, I think p was there, px plus b sine px, and that should be multiplied by e to the power minus p square c square t. Right. Fine. This should be the solution. It is not having any of these conditions on it, right? Fine. Okay. Let me call it equation number 1. You can check that this is the solution. If you check the previous video, you can check that this was the solution, right? Okay. And let me impose these conditions on it. If I impose this condition first, ux 0t, okay, fine. Using this first condition, and for that I have to differentiate it. 0 comma t equal to 0 gives, I have to differentiate it with respect to x, and that will become sine, that will be cos, and that will give me b is equal to 0. I am writing that directly, and you can verify it. That will become sine, and that goes to 0. I'm putting x equal to 0, and that goes to cos 0 becomes 1. That will give me bp times that exponential function equal to 0, and after that I have to take b is equal to 0. You can verify it by yourself, right? Verify. Fine. And now since b is equal to 0, should I put this b is equal to 0 here? Then my refined solution will become, then first becomes u x comma t, and b is 0, a cos p x e to the power minus p square c square t is the solution. New solution, refined solution with a lesser number of constants. Now I should impose this condition number 2 on it, using condition second, and that is actually u 2 pi comma t equal to 0. And what does it mean? I have to put x equal to 2 pi, and okay, t equal to t, and that is equated to 0. Gives a cos 2 pi p e to the power minus p square c square t equal to 0. Now you can see that if you take a is equal to 0, that will produce a 0 solution from equation number 2. And if you take this, where is that? Okay, cos is equal to 0, right? Then we'll get the value of p in terms of n, I think. Okay, and obviously this exponential function cannot become 0. Gives this, and this implies that this cos function, cos is 0 at the odd multiples of pi by 2. If I'm not right. Yeah, right. Multiples of pi by 2, sorry. Pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2. Yes, odd multiples of pi by 2. So I have to write here that cos 2 pi p equal to 0 means this angle is equal to the odd multiple of pi by 2, and I should write it as 2n minus 1, or should I write 2n plus 1 pi by 2, right? Fine. Then this p will be equal to, that 2 will go here, that will be equal to pi will be cancelled, 2n plus 1 by 4, I think. And I should mention what is my n here. n is obviously an integer, right? And that is reduced to n by 2 plus 1 by 4. Fine, that's fine. And it belongs to z. Okay, then I will plug this p in my last solution. And where is that? This is my last solution. And then I will be going to use this third condition. Then second becomes, well, second, this is my second equation, ux comma t equal to capital A, and now we have to write an because now the n enters into my solution, because p should be replaced by 2n plus 1. So the entry of n indicates that the constant should be written with suffix n. An cos, and pi was cancelled, fine, px 2n plus 1 by 4 x, and this is the angle, and where is that? Yes, and e to the power minus p square. I have to square it, or should I write it as pc whole square t? So p c e square c square, and then I have t is solution. And let me check that, is there a need to write n belong to z, or n equal to 0, 1, 2, 3 will work? Obviously negative values of n should not be written here, because cos of negative, that will be positive obviously, and this is also positive for any value of n. So n equal to 0, 1, 2, 3 are possibilities, and if I put n is equal to 0, okay fine, then it is not giving the 0 solution, so I have to include n equal to 0 and infinity. And you should note this step, why I have written as n is equal to 0, right? This is a solution, and what is remaining? Remaining is condition number 3, and let me call it refined solution, solution number 3, using condition number 3rd, and that is given by that ux0 is equal to fx, and let's call it is equal to fx. Ux comma 0 equal to fx, and that will gives here fx equal to, and if I put n equal to 0, then that will be a separate constant, as we have written in previous example. I think putting n equal to 0 will give me a naught here, and summation runs from n equal to 1 to infinity, and a n obviously cos 2n plus 1 by 4 x, and it was 0 goes to 1, fine. So this is fx, and now the Fourier series, a naught is given by the formula and a n given by another formula. Let me calculate a naught here. Then a naught equal to, remember the formula, 1 over capital L. Capital L is the length of rod, this time that is 2 pi, right? Okay, fine, 1 over 2 pi, and integration 0 to L, 0 to pi, fx dx. And what is that fx? Fx is that much, fx dx. I should split this, 1 over 2 pi, first is 0 to pi, and for that I have that x dx plus then pi to 2 pi, and I have 2 pi minus x, 2 pi minus x dx. And now I have to integrate this. Integration will give 1 over 2 pi x square by 2, that is pi square by 2, and integration this will give me 2 pi x minus x square by 2. Let me write it here, 2 pi x minus x square by 2, and on putting limits, if I put 2 pi here, then this will become 4 pi square minus 4 pi square by 2 upper limit, minus pi here, that will give me 2 pi square minus pi square by 2. I think 4 pi square by 2, that will be 4 pi square by 2, 2 pi square cancelled, pi square by 2 plus pi square by 2, if I am not wrong. I have done that directly. right? Okay, 8 pi square by 2, 4 pi square by 2, fine, plus pi square, fine, and this will become pi square. So ultimately that will become pi by 2, I think. This will be a naught, right? And now an and an is equal to 2 over L. L is the length of rod, and that is this time 2 pi integral 0 to 2 pi, and fx cos, what is that? Yeah, cos 2n plus 1 by 4 x dx, right? And then you have to plug that fx, so it will become 1 over pi and 0 to pi and x cos 2n plus 1 by 4 x dx, and the second integral will be pi to 2 pi minus x, and then cos 2n plus 1 by 4 x dx, right? And I have to apply by parts for these and this and this. So that will give me, let me take it I1 and I2, otherwise that will be complicated. I1 say plus I2 say, we'll evaluate them separately. Let me call it equation number 4. Yeah, 4, fine. Where I1 is equal to 1 over pi, this integral, and applying by parts x, and integration of cos is sine 2n plus 1 by 4 x over 2n plus 1 by 4, and then minus 1, and integration of sine will be cos minus cos 2n plus 1 by 4x over 2n plus 1 by 4 whole square, fine, and this is 0 to pi. Let me see what happens if I put pi here, 1 by pi. If I put pi here, then this will become 2n plus 1 by 4 pi, and that will become n by 2, pi n by 2 plus pi, and this will go here 4 pi over 2n plus 1 times sine, and putting pi here will give me 2n pi, that will be 2n pi plus pi by 4, 2n pi by 4, and that will become n pi by 2. Okay, fine. Right. And here if I put pi, that will give me plus 2n plus 1 by 4 square, and this will become cos again n pi by, and that should become n pi by 2, I think. N pi by 2, yeah, n pi by 2. N pi by 2 plus pi by 4, fine. And on putting 0, this will be 0, but that is not 0. This was upper limit, and then on putting 0, I will be getting minus of this will be 0, then this will be minus plus, and then again will become minus, and cos 0 will become 1, and this goes, and okay, I think this should be reversed, 4 upon 2n plus 1. 4 upon 2n plus 1, and that will become 4 upon 2n plus 1 whole square. So this is the value of this I1, right? And similarly we can find I2, and that is this integral, right? Right, fine. And then on finding this a0 is already found, then on plugging those I1 and I2 here in an, I will be getting my full solution. That is my solution number 3, and let me complete that. Okay, and I2 is equal to integral pi to 2 pi minus x, and this is cos 2n plus 1 by 4 x dx, fine. And let me apply formula. Where is it? 1 upon pi. No, this is not 1 upon pi. Fine. Okay. 2 pi minus x, integration of this thing will be sine 2n plus 1 by 4. I think that will be x over 2n plus 1 by 4, and minus differentiation of this will be minus 1 and minus cos 2n plus 1 by 4 x over 2n plus 1 by 4 whole square. Fine. And limits are pi to 2 pi, but this time the evaluation of limit will be easy, because on putting 2 pi here will give this 0, and 2 pi here will give me minus minus plus and then minus 4 upon 2n plus 1 whole square, and this will be 2 pi here, and it will become pi, and 2 here, cos 2n plus 1 by 2 pi, so it will become pi here and by 2. Fine. And it is 0, I think, odd multiple of pi by 2, that goes to 0. Fine. Yes, so I should remove this term, this will become 0. Fine. And now comes the lower limit. If I put pi here, find pi here, then I will be getting minus sign outside it, and here I will be having pi, and here I will be having sine 2n plus 1 by 4 pi, similar to this one, right? And then this goes the n pi by 2 plus pi by 4. Fine. And what about this 4 pi upon 2n plus 1? Fine. And on putting pi here, I will be getting minus minus plus minus minus sign minus, and pi, if I put pi here, then it will become 4 upon 2n plus 1 whole square, and this will become cos 2n plus 1 pi by 4, right? And that pi by 4 will enter inside, right? So 2n pi by 4, that will become n pi by 2, and plus pi by 4. I think this is fine. Okay. And then this minus will go inside, and that will become minus, and that will become plus. So I will put a plus here and minus here. So that will be my I2, right? And on plugging this I1 and I2 here, and if I add these two, yes, this will be cancelled, I think. This term will be cancelled. This term will be cancelled, this term with this term. And on adding these two terms, where is that? This one. These will be added, fine, twice. And this will, okay. So on plugging this I1 and I2 here in my equation number 4, therefore an becomes 1 over pi is outside, and remember that. So this pi will be fine, 1 upon pi will be outside, and 1 upon pi gets multiplied with these things, 1 upon pi, and this will become twice, right? And this is also 16, and 16 plus 16, 32. So I'm writing that 32 over that 2n plus 1 whole square. Fine. Okay. And this is cos n pi by 2 plus pi by 4, and this term minus, and that for that term we have 1 upon pi waiting outside, so that will be 16 over 2n plus 1 whole square pi. I think I am correct. So this is my n, and then my solution was, I have erased that solution, and on plugging this a naught, where is that a naught? Here I had that a naught, right? And this n in my solution, that should be my required solution, right? So that's it for this video. We have already discussed two cases. One was in previous video when the ends of the rod were kept at 0 temperature, and for this case both the ends were insulated. However, I have taken one example, last example, when one of the end was insulated and the other end was at 0 temperature. This is an example for that. That's it for this video. Thanks.